Okay, in this video I'm going to be going through every question that has been asked about bounds. Now if you want to use this document, it is always linked in the description and it's fully hyperlinked, which means you can click through and it will take you between the different questions and the answers. So this one is from a non-calculator paper. The first part is not to do with bounds, but the second part is. So let's read what we've got here. A factory makes 450 pies every day, and the pies are chicken pies or steak pies. Each day Milo takes a sample of 15 pies to check, and the proportion of the pies in his sample that are chicken is the same as the proportion of the pies made that day that are chicken. On Monday, Milo calculated that he needed exactly 4 chicken pies in his sample. Work out the total number of chicken pies that were made on Monday. So I think this is the most important bit that we've got here. The proportion of the pies in his sample that are chicken are the same that are made by the factory. So in his sample, the amount that are chicken are 4 out of 15. That's the proportion. But in the factory, if we're going to say the number that are made of chicken pies that day are going to be X, it would be X out of the total amount that are made. So this is the proportion in the sample and this is the proportion in the factory, and we want to find out how many of them are chicken. Now there's various ways of doing this. You could think, okay, how do I go from 15 to 450 and do the same on the top? Or you could do multiplying by 450. I think probably the way that I would think about this one is that I would say if I multiply both sides by 450, I would find out what X is equal to. Now all this thing is really saying is find 4/15 of 450. Sometimes people like to think of it as a fraction like this, where you would multiply them and divide it by 15. I think the way my brain sees this is if you're finding 4/15 of a number, is you're going to take that number and divide it by 15 and then times it by 4. So I'm going to divide it by 15 and then times it by 4. If I see how many times 15 goes into 450, well 15 goes into 45 exactly 3 times, so that is 30, and then I'm going to do the 30 multiplied by 4, and 30 multiplied by 4 is obviously 120. So this means that X is equal to 120, meaning 120 chicken pies were made on Monday. Here's the bounds part of the question. It says, on Tuesday, the number of steak pies that Milo needs in his sample is 6 correct to the nearest whole number. So he's done some rounding with this. Milo takes at random a pie from the 450 pies made on Tuesday. Work out the lower bound of the probability that the pie is a steak pie. So the probability that it is a steak pie, if it was 6, would just be 6 out of 15. That would be the probability of it being a steak pie. But because 6 has been rounded to the nearest whole number, that means that it could be 5.5 out of 15, or it could be 6.5 out of 15. Now, because we're looking for the lower bound, we're going to pick the 5.5 out of 15, and we're just going to make that become a probability, meaning like a fraction that doesn't have a decimal. So I'm going to double the top so that I get 11, and I'm going to double the bottom so that I get 30. So this is going to be my lower bound of the probability. This would be the probability if it wasn't rounded, but this would be the lower bound because it's as small as it can possibly be. So let's check the answers of 120 and 11 over 30. So we've got 120. It says 165 over 450 or equivalent. So I'm just going to show you that 165 over 450 is actually 11 over 30. So we have got that one right. Now this is kind of like the typical bound questions that we'd come across. So that first one was a bit strange. It says here the petrol consumption of a car in litres per 100 kilometres is given by this formula here. Nathan's car travelled 148 kilometres, correct to 3 significant figures. The car used 11.8 litres of petrol, correct to 3 significant figures. And Nathan says, my car used less than 8 litres of petrol per 100 kilometres. Could Nathan be wrong? You must show how you get your answer. Well, Nathan could be wrong if our upper bound is more than 8. If our upper bound is more than 8. Now, there's no point in checking out the lower bound because he thinks that it's less than 8. So I'm trying to I'm going to say, like, what would it be if he was wrong? It would be wrong if the upper bound was more than 8. So in order to calculate the upper bound of something that looks like this, you want things in the numerator to make them as big as possible. You want things in the numerator to be big and things in the denominator to be small. That's how you get the overall upper bound. You don't want to do big and big. You don't want to do small and big. You want to have the top being as big as possible and the bottom being as small as possible. Even if you just compare something like, I don't know, 10 divided by 5 versus 5 divided by 10, clearly the bigger you make the numerator and the smaller you make the denominator, you get a bigger number. This is 2 and this is 0.5. So that's kind of the logic behind this bit that I've got at the top. So for the number of kilometres that have been travelled, we've got 148. The kilometres are going on the bottom, so I want that to be as low as possible. So I'm going to do my kilometres lower, and that is going to be 147.5. That's the lowest thing that it could be rounded to three significant figures, if it's going to be rounded to three significant figures. And then the petrol, which is going in the top, the litres of petrol, I want to be as big as possible. So I'm going to do my litres upper, and my litres upper are going to be 11.85. Now, putting this all together into my petrol consumption formula, this is going to give me my petrol consumption, my upper value of what this could be. So that's going to be calculated by doing 100 multiplied by the number of kilometres used, the number of litres of petrol used, which is 11.85, and I'm going to divide that by the number of kilometres travelled, but the lower bound of that. Just going to be a case of putting this into the calculator and seeing what we get, and we want to see if it's bigger or smaller than 8. So we're going to do 100 multiplied by 11.85, and we're going to divide that by 147.5. And when I press the SD button, we get that this is equal to 8.03389, etc. So now we just need to say, could Nathan be wrong? Yes, he could be wrong. He could be wrong, as the upper bound is more than 8. Now, if he just substituted the original values into the question, that's why he thinks that it's going to be less than 8. If you subbed in just the 148 and the 11.8 in here, you'd get that it was less than 8. But if you play around with these numbers and you use their lower and upper, you do come up with this thing that we have here. So let's see that we've got this right. Yeah, there's the 8.03, they need it with the 2 decimal places, and we say that he could be wrong. Okay, this time it's just going to be some substitution into a formula. And it says that d is equal to u squared over 2a, u is 26.2 to 3 significant figures, and a is 4.3 correct to 2 significant figures. And it wants us to calculate the upper bound for the value of d. So sometimes people do these little letters to say that this is the upper bound of d, and it wants our answer correct to 6 significant figures. Well, the upper bound of d, if we're using this formula, we want the numerator to be as big as possible. So I'm going to do the upper bound of u, and we want the denominator to be as small as possible. So that's going to be the lower bound as a. Remember, to make something as big as possible, big up here, small down here. So I need to find out what u is as the upper bound of u. So I'm going to say the upper bound of u, it's 26.2 to 3 significant figures, so that would be the upper bound. The lower bound of a, well, that's 4.3 to 2 significant figures. The lower bound would be 4.25. So the upper bound of d is going to be 26.25 squared divided by 2 multiplied by a, which is 2 times 4.25. And we're going to give this answer to 6 significant figures. That's a lot of significant figures. So 26.25 squared, 2 times 4.25, and we're going to press the SD button. So it's going to be 1, 2, 3, 4, 5, and then the 6th significant figure is going to be a 2 because the 7 makes it round up. So that's our upper bound that we've got there. It then says that the lower bound for D is 78.6003 correct to 6 significant figures. By considering bounds, write down the value of D to a suitable degree of accuracy. You must give a reason for your answer. So at the moment we're saying that D is somewhere in between 81.0662, and actually it probably wouldn't have this line, but don't worry too much about that. And the lower bound is 78.6003. So we just need to think, what value would D be that kind of suits both of these? And I think the value that we're going to say is that D is going to be equal to 80, and that's because both of these to one significant figure round to 80. So D is equal to 80. Both the bounds round to 80 to one significant figure. Let's see if we've got this one right. So we've got our 80.0662 and we've got 80, and the bounds agree when rounded to 80, or the bounds agree to the nearest 10, or we could say to one significant figure as well. Okay, we've got another substitution question. It says D equals 1/8 C cubed. C equals 10.9 correct to 3 significant figures. By considering bounds, work out the value of D to a suitable degree of accuracy. So we're going to work out the value of D lower, and then we're going to work out the value of D upper, and then we'll do the same thing that we just did on the previous page. So because we're using C, I'm going to see that the upper value of C is going to be 10.95. and the lower value of C is going to be 10.85. So when I want to do the lower value of D, I'm going to do an eighth times the lower value of c cubed. And for this one, I will do it with the upper value of c, and that one will be cubed. And then we're going to compare those answers and give it to a suitable degree of accuracy. So I'm going to type in 1/8, and then in my brackets, 10.85 cubed. And so that, when I press the SD button, we have 159.661140. Just in case I need those numbers, I've got them. I'm going to then jump back through my calculator. I'll change that to a 9, and I get 164.1165 ... Now, looking at both of these numbers, I need to think, what would they both round to? Well, I think to the nearest 10, or to two significant figures, they are going to both round to 160. So I'm going to say that D is equal to 160, and I'm going to put in brackets to two significant figures. I'm just going to say they both round to 160 to two significant figures. Or you could say to the nearest 10. Let's see if we've got this one right. So we've got the 160, and they both round to 160. You didn't even need to say that they needed to round to two significant figures. We've got another substitution. The time period t seconds of a simple pendulum of length L is given by this formula. Katie uses a simple pendulum in an experiment to find an estimate for the value of g. Here are her results. Work out the upper bound and the lower bound for the value of g. Use pi equals 3.142, and you must show all of your working. Well, unfortunately, this formula doesn't even tell us what g is, so I think we need to do some rearranging first of all. Now, I think what we should do is, first of all, divide by 2 pi, so that I have just root L over g. So I'm going to rearrange it to make g the subject. Make g the subject. So I'm going to divide by 2 pi. I'm going to get t divided by 2 pi is equal to the square root of L over g. Now I'm going to square both sides, so I get t squared over, when you do 2 pi squared, you get 2 squared, which is 4, and then you get pi squared, and that is equal to L over g. Now you can take the reciprocal of both sides. We can flip both sides over, so that's 4 pi squared over t squared is equal to g over L. I do my L's a bit curly so they don't look like ones. And then I'm actually going to just shrink this down so that I can fit it all in one space. I'm then going to just make g the subject by multiplying by L. So I'm going to say that 4 pi squared over t squared multiplied by L is equal to g. And I'm going to use this formula to help me find the upper and lower bounds. So I have my values of L and my values of t. If I want g to be as big as possible, here is my formula for g. If I combine that all together, it is 4 pi squared L over t squared. If I want to do the g upper, I'm going to want L to be an upper and t to be a lower. So g upper is going to be 4 pi squared. L I want to be an upper, and t squared I want to be a lower. And then when I do my g lower, it's going to be the other way around. I want the top to be as small as possible, so that's going to be L lower, and I want the bottom to be the upper value that we've got. So substituting these in, my values of L upper and lower, let's say what they're going to be here. The upper and the lower is going to be, the upper is going to be 52.05, and the lower is going to be 51.95. For t, if we do the upper and lower, the upper is going to be 1.455, you go that little half bit up, and then 1.445 for the lower that we have there. So when I sub them in, I'm going to get 4 pi squared multiplied by the L's upper, which is 52.05, divided by t's lower, which is 1.445 squared. And I'm just going to write the working out for this one as well. We're going to have 4 pi squared multiplied by this one's lower, which is 51.95, divided by the other one's upper, which is 1.455 squared. And then those are going to be my answers for the upper and lower, which I'm actually just going to put straight here into the upper and lower bounds. Okay, so onto my calculator, and I'm going to try and do it so I can just change the values nice and easily. I'm going to do my 4 pi squared multiplied by 52.05 divided by 1.445 squared. So that is 900, if I just get the pen right where I need it, that is 984.1125 ... The lower bound is if I change these numbers. So I'm going to make this one as big as possible, so that's 455. And I'm going to make this one as small as possible, which is the 51.95. So 51.95, and we get that the lower bound is 968.766 ... So let's see if we've got these right. We've got 984 and 968. 984 and 969.01. Oh, I must have typed something in wrong there. Let's see what I might have typed in wrong. 51.95, I want that to be the lower. Yeah, that is the lower, and that one is the upper. Let me just double check if I've typed it in correctly, because that's strange. I've got my 4 pi squared times 51.9 over 1.55 squared. How strange. I will come back to that one in a second and see what's different about that, because it does say... Oh, it does say or. Okay, it does say or, so that's okay. The upper bound, the lower bound, I could have 968.7669. How strange. I will come back and try and figure out why it's got these two different ones. It might be something to do with the rearranging that's happened. So we're definitely going to say these are the two things that we've got. That was very strange they've got these two answers, but ours would be accepted according to the mark scheme. Okay, Jackson is trying to find the density in grams per centimetres cubed of a block of wood. The block of wood is in the shape of a cuboid. We've got these three lengths correct to the nearest millimetre, and he measures the mass as 1970 grams correct to the nearest 5 grams. By considering bounds, work out the density of the wood. Give your answer to a suitable degree of accuracy. You must show all your working and give a reason for your final answer. Wow, because they want it to be a suitable degree of accuracy, we're going to have to do the density upper and the density lower. So I think what we're going to do to begin with is we're going to remind ourselves that our formula for density from our mass density volume triangle that we have, density is the mass divided by the volume. So if I want to do the density upper, I'm going to do the mass upper divided by the volume lower. And if I want to do the lower bound of the density, I want the top to be as small as possible and I want the bottom to be as big as possible. I'm going to begin by finding the lower bound of the volume, and then I'm going to find the upper bound of the volume. These have all been to the nearest millimetre, in other words, to the nearest 1 decimal place. Nearest millimetre is the same thing as to 1 decimal place because it's in centimetres. So for the lower bound of the volume, it's going to be 13.15 multiplied by 15.95 multiplied by 21.65. Those are the lower bounds of all of these three things that we've got here. And then I'm going to do the upper bound would be our 13.25, our 16.05, and our 21.75. Notice how each time it's gone like an extra 0.5 above and below for all of the numbers, and that's going to give me the upper and lower of these. I'm then going to find out what the mass upper is and what the mass lower is. So the mass upper, if it's 1,970 grams to the nearest 5 grams, we're usually going up and down like a 0.5 somewhere, but because it's rounded to the nearest 5 grams, we're actually going to go up and down 2.5 grams. We always do a half of what it is that we're rounding to. So here it's like 1 decimal place, we're going up and down over 0.1 each time, at half of a 0.1. This time we're going to go up and down 2.5 grams. So the upper bound is going to be 1972.5, and the lower, if I take away 2.5, is going to be 1967.5. So using these two formulae that we've got here, I'm going to now work out the density's upper bound. The density's upper bound is going to be the mass of the upper, which is 1972.5, divided by the volume's lower, which is 13.15 times 15.95 times 21.65. And I don't actually even have to work out what the volume is. I can just have that kind of written straight into my calculator like this. So that's 1972.5 over 13.15 times 15.95 times 21.65. And I get that the density's upper is, let's hope it's in the right thing, good, 0.43438285. I'm just going to write a few of those. Now I'm going to do the density lower, and actually the density lower I've got written up here, so I'm going to grab that, put it in the right location, which is down here. I'm going to do the exact same thing before, but with the other bound. So I'm going to do my 19675, that's the lower of the mass. The upper of the volume is going to be 13.25 times 16.05 times 21.75. So much typing in the calculator for this topic. Now, if I actually go through here, I can probably just change some of the numbers. Am I going to do that? No, I'm going to just start it again. So I'm going to do 1967.5 over 13.25 times 16.05 times 21.75, and that gives me 0.4253677 ... So we're going to actually say what the density is equal to. So I'm going to say that the density is equal to, if you compare both of these numbers to two decimal places, they're both going to be 0.43. So I'm going to say that the density is 0.43, and we were doing here the mass, which was in grams, divided by the volume, which was going to be in centimetres cubed. So it is 0.43 grams per centimetres cubed, and I'm going to say both the bounds round to this, to two decimal places, round to this, to two decimal places. Let's see if we've got this one right. This was a huge question, but it was a 5 marker, which is the highest it can be. So we've got that 0.43, and it is to two decimal places. You could have said two significant figures as well. Okay, now we've got them with speed, distance, time. So as soon as I know it's speed, distance, time, we're going to say that we have our distance, speed, time like this. And it says a train travelled along a track in 110 minutes, correct to the nearest 5 minutes. So it's a bit like the previous one where the grams, we went up and down 2.5. We're going to do the same in this one. Jake finds out that the track is 270 kilometres long, and he assumes that the track has been measured correct to the nearest 10 kilometres. Could the average speed have been greater than 160? So it seems like we're interested in finding the upper value of the speed, because we're trying to say, could it have been greater than 160? Now the upper value of the speed is going to be found by doing the distance divided by the time. Now we're always wanting to make the upper bound. We want this to be as big and this to be as small as possible. So I'm going to do the distance upper divided by the time lower. Well, the distance upper is going to be, the maximum that could be is 275, and the time lower, it's 110 minutes to the nearest 5 minutes. So I'm going to do 110 take away 2.5, which is going to be 107.5. Now, interestingly, this is going to give us the speed in kilometres per minute. So afterwards, we're going to need to convert it into kilometres per hour. So I'm going to do 275 divided by 107.5, and that gives us that the speed is 2.5581, but that is in kilometres per minute. Kilometres per minute. Now, because I want it to be in kilometres per hour, I'm going to times it by 60, and that's going to give me my correct answer. So here is what I've got. I'm going to times that by 60, and we get 153. We get 153.48 kilometres per hour. So it said, could the average speed have been greater than this? No, the average could not have been greater. The average could not have been greater. It can't have been greater than 160 because it can't have been greater than 153.48. It says Jake's assumption is wrong. The track was measured correct to the nearest 5 kilometres. Explain how this could affect your decision in part A. Well, if it was measured to the nearest 5 kilometres, this would actually be 272.5, which would actually make it even smaller, so it wouldn't change it. So explain how this could affect your decision in part A. It would actually reduce the speed. It would reduce the speed further. It would reduce the upper of the speed even more. So the decision is the same. And if you wanted to, you could literally just try it on your calculator. You could replace that 275 that we've got with 272.5, and we could still divide it by the 107.5. And you'll see when you times that by 60, it's even lower. It's now gone down to 152. So I'm going to look out for that 153.48 and see if we've come up with the right thing. There's the 153.48, so that's why it was a no. Less distance in the same time, so the maximum speed would drop. That's exactly what we've said. Okay, we've got another speed distance time. A high-speed train travels with a distance of 487 kilometres in 3 hours. The distance is measured correct to the nearest kilometre, and the time is measured correct to the nearest minute. Weird. So we've got 3 hours. As soon as they say nearest minute, I want to remind myself that 3 hours is 3 times 60, which is 180 minutes. That's definitely going to be used in the question. By considering bounds, work out the average speed in kilometres per minute of the train to a suitable degree of accuracy. show all of your working and give a reason for your answer. So we're trying to work out the average speed. Quick reminder that speed is distance divided by time. So I'm going to do the speed upper, and then I'm going to do the speed lower. So the speed upper, remember it's distance over time, so I'm going to do the distance divided by time. Now this one I want to be the upper and that one I want to be the lower. If I'm doing the lower, I'm going to do the distance lower divided by the time upper. Remember, you're always trying to make small things on the top and big things on the bottom if you want it to be small overall. So the distance upper, if it's to the nearest kilometre, is going to be 487.5, and the time lower to the nearest minute would be 179.5. The distance lower would be 486.5, and the time upper would be 180.5. Now, they do want it in kilometres per minute, and this is in kilometres and this is in minutes. They don't want it in kilometres per hour. That means we can literally just type these in straight away to the calculator. So I'm going to do 487.5 over 179.5, and we get I always don't have the right pen feature on, we get 2.7158774. I'm just writing down a few numbers because it might be useful for the rounding part. 486.5 over 180.5, and we get 2.695290 ... So what do they both round to? I would say to two significant figures or to one decimal place, they both round to 2.7. So I'm going to say that the speed is equal to 2.7 kilometres per minute. And the reason I'm going to say that is the bounds both round to 2.7 to one decimal place. Or you could say two significant figures. So let's check we've got the 2.7 there. We do have the 2.7, and we have the 2.695 and the 2.715, the 2.715, the 2.695 that we've got there. Okay, this I think is the last one. Yes, it is. And this one has got some stuff to do with 3D Pythagoras. It says the diagram shows a cube. AH is 11.3 centimetres correct to the nearest millimetre, which is the same as one decimal place. Now, AH is this line, this diagonal line between A and H that we've got there. Now, I'm not going to go into the details of this, but the way that you do the diagonal of a cube is a bit like Pythagoras, but just with 3 parts to it, rather than 2 parts to it. Now, all of these parts that we have of this cube are x centimetres, so you can see all of these parts are going to be x. We want to calculate the lower bound for the length of an edge of the cube. Okay, well, usually we would say that AH is equal to, it's like Pythagoras with the 3 different parts, it is going to be x cubed plus x, not x cubed. Like Pythagoras, it's going to be an x squared plus an x squared plus an x squared. This is how you do Pythagoras in 3 dimensions. Now, because I want to find a lower bound for the edge of the cube, I'm actually just going to rearrange this to see if I can find out what x would be equal to. So first of all, I'm going to square both sides so that I get my AH squared. That would be equal to x squared plus x squared plus x squared. That is equal to 3x squared. Now I'm going to divide both sides by 3 so that I get AH squared divided by 3 is equal to x squared. And then when I make x the subject, it is the square root of AH squared divided by 3. And I want to find the lower bound of this. So if I'm looking for the lower bound of x, I'm going to use the lower bound of AH. So the lower bound of x is going to be the lower bound of 11.3, which is 11.25, and that is squared and then being divided by 3. I'm just going to find out what it is on the calculator, which is on this side. So I'm going to do the square root of 11.25 squared. Let me just get that as a fraction for a second. 11.25 squared over 3. And we get that it is, what do they want it to? You must show all your working. I'm going to write lots of these numbers down. Let me get the pen feature back on, and I'm going to say that it is 6.495190. That's definitely enough that we've got there, okay? Let's see if we've got this one right. There is the 6.495190. Is that what we had? Yeah, 5190. So that is all of the questions that have been asked on bounds. There's a lot of them there, and you really do need to be good at deciding which is the upper and lower bounds. If you're not sure about how I did these, they're to do with error intervals. So go and ask your teacher about that, or you can go and look at some of the earlier ones I've got here about rounding and estimation, because they kind of go through those as well. If you did find this useful, I would really appreciate you just liking the video or considering subscribing to the channel. It just helps other people come across it, and that's really just what I want to happen so that people can get as much as they can from their revision.